Working?
I don't know, guys. Can you hear us? Can you let us know?
Ah, it's a mess with this connection. Was bad, ma era meglio quando lo facevi da dipartimento? Ci fanno parlare, ci ascoltano. Funziona? Ah, ecco. È meglio se mi disconnetto? No, tanto non serve. No. Ok, can go again. Ok. Okay, sorry for the interruption. The problem, we had a problem, but now it's solved. As already said, as trying to explain you, with this method, we would like to understand if a social network is associated a certain image. What can we done? Extracting some feature from the image from the image itself through the use of in this case DCT-based feature that are able to understand if an image is single or double JPEG compressed. Because if it's single compressed, it is not wasn't uploaded on a social network before. But if it's double JPEG compressed, this image most probably was uploaded through a social network, and in particular understand which social network. This kind of feature regarding the noise residual is more about understanding if an image was resized or not. This is the same idea behind the photo response non-uniformity noise, and is also about the question that one of you give it to me, because if we resize an image, so this resizing interact in the PRNU. And so it's possible to exploit this to understand if an image was resized or not. This kind of feature was then given to a FusionNet, a CNN-based framework that is able to understand the social network and the instant messaging application class related to a certain image. So we apply a dual model feature for image representation. So the histogram of the DCT that I showed you before, and the sensor noise residual. And also, and then we gave these two input to two CNN branches. And it's really some layer can be a UGG16 or something like that, an architecture that is well known. And then we fuse together the activation vector came from these two CNN branches. And after diffusion, it's possible to classify the source social network and also the instant messaging application of the images in question. Here we have some results. We tried different data sets. Some of these data sets was made by us. We constructed the data set by ourselves because it didn't exist before this kind of data set. So it's possible to see from this table that the classification is good on all the two data sets. But in this case, we solve one of the problems that we would like to solve. So we are able to understand if there was a single share. That means we have an image, we upload on Facebook, then we download again, and then we classify. So there is only one share on one social network. What we want to do, and this is good, so the results are good on this task. But if we would like to solve the other task, so understanding all the share that an image undertake during its life. For example, the image for the first time is uploaded on Facebook, then uploaded again on Twitter, and then on Flickr. We consider these three social networks for this case. What we would like to understand is all the history of the image. So if an image is shared on Facebook, Twitter, and Flickr, and that's it. This is a little bit more difficult. Again, we are able to solve the last problem, so we understand the last social network of the chain, and somehow also the other share, the previous share. So we are able to understand with a certain accuracy that the image is coming from Flickr in this case.
So we have a question, which is, aren't these results depending on the compression algorithms used by all those companies? Is this method robust to compression algorithm changes?
Yes, this is a good question. Yes, depends from the compression algorithm used from the different social network. So, but on the other side, no, is not robust if this algorithm change. In particular, is not somehow related, so can be robust a little bit. It's not somehow related to a certain algorithm, but is related to the kind of double JPEG compressed performed by the social network. Related to the quality factor to this social network recompress the image. For example, if we have our image at the beginning is not double JPEG compressed, so maybe the quality factor at the beginning is, I don't know, is the maximum, so it's 100. But again, when it is uploaded, Facebook perform a double JPEG compression, a certain quality factor that compress more the image. So let's say 70 quality factor. And so with this method, we are able to understand this kind of things. So if this method changes this fact, we are not able to say something about the double JPEG compression, but there are the other features that maybe can help us, for example, regarding the resizing and so on. And as I show you later, regarding some information and some feature regarding the metadata, for example. In fact, to solve this multiple share classification, we employ also this kind of feature coming from not only image-based feature, but also metadata-based feature that we see that is more robust to the multiple share. Hopefully I answer to the question.
Okay, so the question is, won't the image editing from the in-app features throw off the prediction?
No, I cannot hear you.
Can you hear me?
Wait a little bit. Repeat, please.
So can you hear me?
No.
No?
Okay. Yes. Yes. No.
Okay,
Yes.
okay. So the question was, won't the image editing from the in-app features throw off the prediction?
The image editing. Yes, of course. Image editing, yes, can be a problem, of course. No, we didn't check this point because the task it's already difficult enough. So we didn't check with editing with the image that is manipulated in some way. Um, okay, but I'm expecting that the robustness can be lower a lot. Okay. Uh, Okay, regarding this multiple up-down classification, we perform the CNN as before, but we insert this kind of metadata-based feature here at the for the multi-layer perceptron classifier that help us in this more difficult task. But the problem is the same. At the end, we would like to understand the prediction related to an image related to a class. Let's say a social network or instant messaging application. Again, we have different data sets, and we analyze up to 3 share. So in the class 1, we have 3 classes. In the first share, I'm sorry, we have 3 classes. This is the case as before, so the single share. The in the second share is we have 9 classes to classify, and in the, up to the 3 share we have 39 classes. So the classifier and our network is able to classify up to 39 classes that take in account all the different share among the different social network and also the single share and the double share. We build 2 different data sets. Now, if you want the detail about the data set, you can go and the paper and read the paper for detail. Here, I report only some results. Of course, in the case of single share, as before, the accuracy is good, but when we have the double share. The accuracy decreased, but it's still good. This is the second column here, C2 columns. At patch level, in image level for the 2 data sets that we take in account. Here we have some confusion matrices of the results, where we have the true label. Here is the results for double share, the true label and the predicted label. We can see that the results are satisfactory, but sometimes the results are completely wrong. For example, here in the second matrix 6, we have for the true label was Twitter, and the predicted label wasn't. The classifier, the network wasn't able to predict the label. In fact, the percentage here is 0.22. But if you see all the other contribute here, that is not 0 in the matrices, we can understand that the predictor label here was spread. The contribution of this point was spread in this column, that in this row, that was Facebook and Twitter. So the second social network was Twitter again, and also Flickr Twitter again, or Twitter and Twitter again. So the point is that this contribution, this prediction was classified with classes that are related to Twitter, at least at the second share. Okay, for triple share, the results are more complicated to read, and so we aggregated the 39 classes into 21 classes. For example, the case Facebook, Flickr, we consider as Facebook, Flickr, and Flickr, Twitter as Flickr, Twitter. So if we see this picture, it's possible to see that some result is possible to obtain also for triple share, not so good. 60% of accuracy is not really good, but is something. If we consider again the last social network, we obtain accuracy of about 98%. Okay, I conclude this part of about the source identification. So if you have some question, very quickly, and then we can go with the second part of the presentation, that is the authenticity verification part, forgery detection part. Ma te non sei online ora? Non sei online ora, di là. Ok, però a me sì. Okay, the second part is about forgery detection. And I would like to start with some definition of the manipulation that we take in consideration in forensics. We consider, we call image splicing when a part of an image is placed in another image in order to obtain some kind of forgery, so some kind of composition of images. We call about copy move manipulation when a part of an image is copy and paste in the same image in order to hide something or duplicated something. And then there is all this kind of new manipulation called deepfake. That means generate convincing audio and video of fake events with AI technique or deep learning technique like generative adversarial network. So the task here is about how can we reveal if an image is manipulated or not. And also we would like to localize this manipulation. So given an image, an input here, we can give an input to some kind of machine learning technique, detector or deep learning technique. And then the output is the image with some kind of confidence of tampering or not, and the localization of a splicing in the image. There are different techniques for tampering detection and can be separated in 4 categories. The first one, I go briefly with this. The first one is the camera-based technique. That is based on the PRNU that I told you about before. Because if you think about it, if we have a tampered image and we extract the fingerprint patch by patch, not this time not on all the image, but patch by patch, it's possible to understand if a patch is related to a certain fingerprint related to a certain camera, and another patch is related to another fingerprint, or otherwise if the fingerprint is inconsistent to the other fingerprint that is present in all the other patch of the images. So it's possible. Yes. Ok, ok, non lo uso più. Posso ripartire? Okay. Another technique to understand if an image is tampered or not are based on illumination, inconsistencies in illumination and trajectory. Illumination is because sometimes when you perform a composition, the light is different with the shade and the light of the image are different on different subject of the image. For example, here we have Brad Pitt and Angelina Jolie with 2 different illumination direction of the light. Regarding the trajectory, it's possible to understand if a video, if we have some motion in a video, if it is consistent with some geometric or physical law, and if it's not, we can understand if this video is fake or not. There are all other techniques that are based on, we call this technique based on format. So we study the double JPEG compression of an image. As already said before, for the social network case, is the same fact, because if we perform some kind of manipulation of an image, the image in the part where it is manipulated is have to double JPEG compression. Instead, on the other side, if the image is not manipulated, the image is compressed only one time. So studying these different behavior in the histogram of DCT coefficient is possible to understand if an image is manipulated or not. There are also other kind of technique that are based on feature, in particular about salient point in particular, I would like to talk about this technique that is a little bit old, but is one of the first techniques that was able to deal with this copy move manipulation. And we build this technique. It was one of the first techniques that apply computer vision technique to a problem that in image forensics was solved only with image processing technique. So it is kind of a different point of view that we introduced back in 2011 in image and video forensics. in particular, we define different data sets because at the time there wasn't a data set for copy move manipulation. And we employ this technique, the copy move manipulation. It's really easy to understand. It is able to hide something if we want to cover something in an image, or we want to duplicate something. If you think about it, when we perform this kind of manipulation, we apply to the patch that we want to move a translation, a rotation, and resizing to the image. So to deal with this kind of transformation to the clone patch, we would like to employ a method that detects such clone and estimate this transformation that is performed on the patches that we want to move somehow in the image. So there is in object and detection and recognition, we used salient points to perform to describe this region with a shift that are scaling variant Fisher transform that are adopted because are robust to this kind of transformation and have high performances in this kind of transformation that are translation, rotation, and resizing. So our copy move forgery detector is composed by different phases. We have the test images on the left. In the first phase, we perform shift feature extraction and matching on the same images. So it's different from shift feature extraction and matching that we use generically for the generic problem of matching between objects, because we want to perform the feature extraction and also the matching inside the same image. So in the second phase, we want to clusterize this point and perform the detection of the forgery. In this phase, we perform clusterization that was performed on geometrical transformation domain. The transformation domain is not spatial domain, because sometimes these points are close to each other, like this, but maybe are not from the same patch, are related not from the same patch, but need to be separated in order to better localize this area. So after we clusterize this point, we apply a geometrical transformation for each of these patches. For example, we calculated the geometrical transformation between this point, this red point and this green point. And then we apply the geometrical transformation to all the image. And so after that, we perform a correlation between the original image and the geometrical transformation, one. And then we segment the image in order to perform the localization. Here there is some results. At the time, there was one of the best methods to solve this problem. The image that I showed you before was actually a real image that we worked with, because there was this picture taken by a photojournalist from Associated Press that was fired from the news agency because this picture was manipulated, was altered by himself. And so we try with our method to understand what happened in this image, and we find out that actually there was some kind of manipulation in the image. And the manipulation was done because in the original image, this one on the top, there was a video camera on the bottom left part of the image. And so the photojournalist covered this part with the background coming from other part, the other part of the image. You can see that this image change is a lot with this kind of tampering. Okay, this kind of method can be also employed for printed images because it's working on features that work on the content of the image.
So we have a question related to what you just said. How does this detection handle the use of tools that copy the pattern and generate a similar pattern to it? Not exactly patch cloning.
Please repeat.
So yeah, how does this detection handle the use of tools that copy the pattern and generate a similar pattern to it, which is not exactly patch cloning?
Yes, this is a good point. The technique is not really robust on this kind of attack. It's more robust if you perform some kind of patch match that is used in, for example, in Photoshop. But if you use some kind of pattern, is no more robust. Okay. Regarding this, we also build an application for smartphone to to extract this kind of to understand if an image was manipulated with this kind of copy move attack. Now let's talk a little bit. This is the last part of my presentation about the new threat that is called deepfake. Exists many techniques to create deepfake right now. There exists a lot, and in the last year there is a proliferating technique on this phenomenon. So it's necessary from our side, that is image forensics or video forensics, understanding if it's possible to say something about this video, if we can say, and it's really a challenge because if at the first time this deepfake was really easy to see also by naked eyes, but now the sophistication increased a lot, and so also the use of deep learning technique that we employ right now are no more sufficient. So we need to study a lot on this topic in the future. Okay, let's talk about different technique for deepfake very briefly. There are two kind of deepfake. We call deepfake generically many different techniques, starting from videographic technique, video rendering technique that extracts some landmark in the face and then create a 3D mask. And also we call deepfake some kind of video generated by deep learning through the use of generative adversarial network, for example. And then we call deepfake some technique like deep face swap. That means we want to swap the image, the face of Donald Trump in the face of Kim Jong-un, and so on. But we call deepfake also some kind of reenactment. That means we apply, we have a source actor and a target actor, and we want to reenact the Donald Trump video with the face, the eyes movement and the lip movement of the source actor. This is the reenactment. Here there is some kind of example, but we can go forward. This is the video that I was working.
No, Irene, can you hear me? Since when you played the video, your audio became completely a mess. We cannot even hear anything. We hear like some voice coming from another word. Probably if you close, I don't know what's going on.
I avoid the video.
No, but even if you speak normally now, it's like you broke your microphone by just doing that, which is of course not true. But
Now it's better?
yes.
Okay, sorry, guys. Next time it should be better.
What happened? Do you know what happened?
Okay, let's go without the video. If you are interested in the video, you can find many of them on YouTube, on the web, so you can go and enjoy with all the video of the fake video. And of course, there is also a proliferation of dataset for forgery detection related to human faces. In particular, there is this kind of dataset called face forensics and face forensics plus plus that consider different technique for deepfake. In particular, 1,000 images for each manipulation method. And also Google and Facebook are working on their dataset on deepfake. So there is a lot of attention on this topic. What has been done since now in literature? First of all the technique employ a face tracking method that is able to extract the region of the image that is covered by the face. Then the region is fed into a classification network. Most of them are deep convolutional neural network, some other deep learning architecture. And then a prediction is performed. The prediction is about fake or real. So the prediction is a binary prediction. And the prediction is done on RGB patches. Different state-of-the-art classification methods are evaluated, and in this particular paper that you can find here was published by Rossler et al. At ICCV last year. They found out that this net, based on exception, outperform all the other networks. What is done since now in literature? All of this technique and also the technique by Rossler et al. Are frame-based. So examine the video frame by frame, and for each frame say something about the fact that is deepfake or is original. And the approaches in general look for spatial inconsistencies in frame, like before, or some other method search for semantic anomalies. For example, sometimes in the deepfake video, there can be the face can have two different earrings, or maybe two different color of the eyes. So if we are able to exploit this kind of semantic anomalies, we find out that a video is fake or not. For example, other method search for eye blinking absence, or some other method want to find out some inconsistencies in the symmetry of the face that maybe you found out in original video, but in the reality, but you cannot find out in the fake video. We think about another approach. We studied this approach in the last year, and also we are on this also right now, because all of the method existing in literature work in a frame-based fashion. But we think about an approach that work on a sequence-based, because we would like to look at possible dissimilarity in the video temporal structure. And we employ optical fields, optical flow fields, to do this. Motion vector optical flow should exploit different interframe correlation between fake and original videos. So we would like to demonstrate this, that the motion vector for a deepfake video and the motion vector from an original video are different. And then this information is used to train a CNN-based classifier. The optical flow fields describe the motion of an object in a scene, and so is well suited to solve this kind of problem. The pipeline that we would like to follow is the following. We use a semi-trainable neural network. We employ two networks for comparison, the architecture of VGG16 and ResNet15, pre-trained on optical flow and not on RGB. And so, and then at the end of this, the last convolutional layer are dense layer are trained, only the dense layer at the end of the net are trained on Deepfake dataset. So it's a pre-trained neural network that is trained on the Deepfake dataset only on the last layer. The test setup is the following. We use the Face Forensic++ for the experiments. Face Forensic++ is composed by 4 different deepfake methods. 2 of them are deep learning methods. 2 of them are graphic methods. We use a patch 300 by 300 pixel around the face, given to the input, to the CNN. The patch, the square patch is randomly chosen and flipped to perform data augmentation. And then here there are some kind of information about the optimizer used and so on. We have some experimental, we've done some experimental results. Here there is some results from the point of view of quality. Here is reported an image, a real image from a video, where we can see, we can appreciate the motion vector around the chin that are more noisy than the deepfake part here, where the motion vector are more smoother. So the characteristic that we would like to exploit in this case is really evident here. Here there is the detail about this. Regarding the results on the dataset, we obtain this accuracy on different compression of the video, and we obtain an accuracy higher than 90% for all the method used for construct the deepfake, to build the deepfake. Okay, now I would like to give you some future trends that then, in my opinion, is necessary to follow in image and video forensics in this area of research area. It's necessary to build an universal method for forgery detection that it is independent from kind of manipulation and compressions, and it is also aware of deepfake, that is able to distinguish if an image is deepfake or not. And it's necessary that this method is also multimodal, because alone, only looking to an image or a video is not sufficient to understand if an image is manipulated or not. Mainly because the image can be compressed, can be every kind of processing. So it's really difficult to understand something only from an image. So a multimodal approach, it's really recommended. So it means you want to have information also from other kind of media. So text, audio, and so on. I would like also to tell you that there is this kind of challenge promoted by Facebook that is investing more than 10 million in grants in this challenge. It's called Deepfake Detection Challenge. So also the big company are really focused on this right now. So that's it. Thank you for listening to me.
Okay, so
some question I can answer.
Yeah, so guys, do you have any questions that you want us to answer? Or actually Irene to answer? I don't I will not answer. So let's yeah, so many people are saying thank you. It was very interesting.
Thank you. Thank you. I'm sorry for the presentation, and sometimes the audio is not working, but I did my best. Try at least.
Okay, guys, so next week we'll have again seminar at the same time. We'll have Abhinav Valada from University of Freiburg giving a presentation on robotics related applications. And yeah, so if you don't have more questions, that's probably it. Thank you very much. Bye bye. Actually, there is a question just on the last minute. So how far are we to have some of these tools available for journalists to use on a daily basis, for example?
This is a good question. Actually, some of these tools are available actually for journalists to say something, but all of them are all of these tools are coming from research. So there's not really tool tested in a real world. So it's more like a bunch of tools that maybe can solve some kind of problem, some kind of manipulation. And then maybe a journalist, there exists a tool that is used also not only for a journalist, but also for law enforcement, that collect all of these methods that are, are the product of research from some kind of university, and employ this kind of tool separately. So we don't exist a method that is able to collect all of them and give some answer in a uniform way.
Okay, thank you very much. And I don't think we have more questions. I don't see any message on the chat. Okay, thank you again.
Okay, bye. Thank
Bye.
you.
See you guys. Bye.